Okay, Michael, you've called my bluff. You said I've left out the most important parts, and you are right. So I'm going to tell you how to construct the most important parts. Let's start with the distribution. So let's start with the base case, and that is the distribution at the beginning of time, d sub 1. So this distribution is going to be over each of the examples, and those examples are indexed, so over I, and I'm simply going to set that distribution to be uniform. So how many examples do we have, Michael? Let's pick a letter. Let's call it n.
Okay.
Why not? Because we do that for everything else. And I'm going to say that for every single one of the examples, they happen 1 over n times. That is, it's a uniform distribution. Now, why do I do that? Because I have no reason to believe, for the purposes of this algorithm, that any given example is better than any other example, more important than any other example, harder than any other example, or anything else. I know nothing. So see if you can learn over all of the examples. You with me?
Yeah, because I feel like if it actually solves that problem, we're just done. So,
yes, and that's what you always want. But that's the easy case. So I start out with the uniform distribution. That's what you usually do when you don't know anything. But what are you going to do while you're in the middle? So here's what I'm going to do, Michael. At every time step t, I'm going to construct a new distribution, d sub t plus 1. Okay, so here's how we're going to construct the distribution at every time step, okay? I'm going to create the new distribution t plus 1 to be for each example, I, to be the old distribution at times t times e to the minus alpha t times y sub I times h of sub t of x of I, all divided by z sub t. So that's pretty obvious, right? So what do each of those terms mean? I mean, I know it's intuitively obvious, even to the most casual observer, but let me just try to explain what each of the parts mean. So we know that the d is our distribution, and it's some number where over all the examples it adds up to 1. And it's a stand-in, we know, because I said this at the beginning, for how important a particular example is, how often we expect to see it. And that's the trick that we're using with distributions. So I'm going to take the old distribution for an example, for a particular example, and I'm going to either make it bigger or smaller based upon how well the current hypothesis does on that particular example. So there's a cute little trick here. We know that h of t always returns a value of either minus 1 or plus 1, because that's how we defined our training set. You always have a label of minus 1 or plus 1. So ht is going to return minus 1 or plus 1 for a particular x of I. Y of I, which is the label with respect to that example, is also always going to be plus 1 or minus 1. And alpha t is a constant, which I will get into a little bit later. Just right now, think of it as a number. And so what happens, Michael, if the hypothesis at time t for a particular example, x of I, agrees with the label that is associated with that x of I?
Well, hang on. You say that alpha is a number. Is it a positive number, between 0 and 1 number, a negative number? What kind of number? Does it not matter? I think it matters.
That's a good question. It matters eventually, but right now that number is always positive.
Positive. All right. So like a scaling, almost like a learning ratey kind of thing, maybe.
It's a learning ratey kind of thing, sort of.
All right. So good. So the y, okay, I see. So the y times the h is going to be 1 if they agree and minus 1 if they disagree.
Exactly. So if they both say positive 1 times positive 1 is 1. If they both say negative 1 times negative 1 is 1. So it's exactly what you say. When they agree, that number is 1, and when they disagree, that number is minus 1. Alpha sub t, which I define below, is always a positive number. You can trust me on this. The error is always between 0 and 1, and it just turns out that the natural log of 1 minus a number between 0 and 1 over that number always gives you a positive number. And if you don't believe me, you should play around with the numbers till you convince yourself. So that's going to be some positive number. So that means when they agree, that whole product will be positive, which means you'll be raising e to minus some number. When they disagree, that product will be negative, which means you will be raising e to some positive number. So let's imagine they agree. So you're going to be raising e to minus some number. What's going to happen to the relative weight of d sub t of I?